All right, this is Geometry A, Unit 6, Lesson 5, I believe. We're talking about special triangles. In this case, we're talking about perpendicular bisector. And we will also talk about isosceles triangles. Okay, but here, let's have a look at the perpendicular bisector situation here. We've got a line segment. Let's do it this way here. Segment AB, and we've got the perpendicular bisector of segment AB. And we're going to say that's segment CD. So CD is a perpendicular bisector of segment AB. Perpendicular bisector means perpendicular, 90-degree angle. Bisect, by two, sect, cut, literally to cut in half or cut in two. And so when we say AD is the perpendicular bisector of AB, we're saying a number of things here. So, or CD, segment CD is the perpendicular bisector of segment AB. Here's what we're saying. We're saying AE, if E is the midpoint, is congruent to BE. AE is congruent to BE. And we're saying that angle CEB, is or measures 90 degrees. The measure of angle CEB, equals 90 degrees. Okay. But what does that mean in general? Let's see if we can extrapolate a little bit what that means. I'm going to draw some external, some other lines. I'm going to draw segment AC and segment BC. AC and BC. And we're going to look at two triangles here. Okay. You'll note that EC is shared by both triangles. Okay. And so I'm going to write a proof here. Okay. I'm going to say AE is congruent to BE by the definition of perpendicular bisector. By the definition of perpendicular bisector. I'm going to say angle BEC is congruent to angle AEC, since all perpendicular or right angles are congruent. Okay. And I'm going to say that CE is congruent to CE. Okay. The name of this rule is something called the reflexive property. By the reflexive property. Anything's congruent to itself. Let's look at what we've got. We've got a side congruent to a side. We've got an angle congruent to an angle. We've got a side congruent to a side. We studied these in the last unit here. That's side, angle, side. Side, angle, side. So therefore, triangle AEC is congruent to triangle BEC by the side, angle, side theorem. Okay. Now, what does that mean? It means the two triangles are the same shape, and they're similar, or they're congruent to each other by reflection, right? One flips over to become the other. Okay? But that's not a proof, that's a demonstration. This is a formal proof that the two triangles are congruent. And we know if two triangles are congruent, then so are all their parts. So by corresponding parts of congruent triangles are congruent by CP/CTC, or the definition of congruent triangles, we know that AC is congruent to BC, or AC is the same length as BC. Okay? And let's see what that means. That means that any point, C is a point on the perpendicular bisector of AB. And it is the same distance from C to A as it is from C to B. So here's what we've just proven. Any point on the perpendicular bisector is equidistant from the endpoints. So I'll give you a scenario. Have a perpendicular bisector. Perpendicular bisector of AB. And I tell you that point C is here, and from C to B is 5 units. Then C to A is also 5 units. Okay? That's what it means. You'll be given a problem like this. Let's go to a new slide here. Let's say you've got a perpendicular bisector situation here. Situation where we know that AB is the perpendicular bisector of CD. Okay, so these are the same and these are right angles. And let's say this is x plus 5 and this is 2x minus 6. You know that these are equivalent, that 2x minus 6 equals x plus 5. Solve by subtracting x from both sides and adding 6 to both sides, and you get x equals 11. Okay, so basically any point that is on the perpendicular bisector is the same distance from the endpoints, no matter where they are. All right, so hopefully that makes sense.